Hello guys, welcome back to my channel. As you see, it has been a long time since I last uploaded, sorry, but there is a lot that has been going on since then. So I decided today to solve some code forces, actually one problem, to tell to you guys and do some then enjoy and such stuff. So the problem today we're going to do is code forces C testing ground 12 subsequences. So it's, as you see, Dp rating 1900. So let's see what it says. So we're given n different elements and we need to count the subsequences, the increasing subsequences with k plus 1 elements. So as you see, of course when you see count, you immediately understand that it will be Dp, the solution. As you see, the constants are n size of array is 10 to the 5th and k from 0 to 10. So let's see. The example says has a sequence 1, 2, 3, 5, 4, and we need to count the number of increasing subsequences with 3 elements as k equals 2. So the answer is 7. Let's see some examples. So it will be one subsequence is 1 to 3, another one 1 to 5, 1 to 4, 2, 3, 5, of length 3, and both increasing subsequences. So let's start with the DP one, the DP solution. So let's denote dpij. Wait, can you see, guys? Let me draw it. Okay, I'll draw it. So, okay, my drawing isn't good. I'm sorry about that. Hope you understand. I will write it down again. So let's denote dpij equal to the count of increasing subsequences. Okay, it's gonna take a long time because I don't have it with drawing or writing in such apps. Oh my god, sorry about that. Actually, I can write it in text if I find it. Wait a minute. Okay, here. So let's denote dpij. Wait, let's erase the above. Okay, let's go back. So let's denote dpij. dpij will be equal to the count of subsequences, increasing subsequences, ending at I, at index I, ending at index I, and having, consisting actually, of j elements. Consisting of j. So that means yes. So for example, we need in a problem to find the number of critical subsequences of length j k plus 1. So j will be equal to k plus 1 in our example, and we need to find, and our answer will be actually the sum of dp0 k plus 1 plus dp0, sorry about that, k plus 1 is the actually dp1 k plus 1 plus dp2 k plus 1 plus until we reach the last index, which is n minus 1 k plus 1. So because that will be the answer for the problem, because dp, as we said, dpi of ij denotes the number of increasing subsequences ending at index I, and are an increasing subsequence end either at 0 index, 1, 2, 3 until n minus 1. So we need to count the total number of subsequences in your example, in your problem. So we need to find for every position, for 0, 1, 2, the number of subsequences ending at this index, that consists of k plus 1 elements, which is j in our example, in our dp, let's say. So I think it will be easy to compute it. Actually, I didn't say that we will do the problem in two versions. That will be like the easy one with dp and compute it like brute force, let's say. But there will be in the other video, the next video I think, we will compute it that optimally with segment tree, and because this solution won't pass obviously at Codeforces, as the n equals like 10 to the fifth, so this will be at least n squared uh, multiplied by k, so which is sure bigger than 1 second, which is TLE of course, for n equals 10 to the fifth. So let's try and do this one, which is brute force. So I solved it yesterday with the other one. This of course didn't pass. So let's yes, I think let's start coding. So I don't know if you can hear my keyboard. I just got a new one. I'll give you guys the link below. So let's see. So sorry about that. Maybe I will erase it somehow. I don't know if I can. I can, never mind. So yes, let's continue coding. We have there, actually we have ni, k, and k actually. So then we have, oops, different elements. Actually, if you know, if you noted, never mind. If you saw in the problem, it says we have n different numbers, different. So that means that will help somehow. Yes, that will help in the second solution, the optimal, with segment tree, because we need to store positions. And in order to store positions, if there are multiple elements, it will be really hard with pairs and that. So if they're different, we can just have a map and do position of element here. So if there are different, position of element x will be unique for every x in the array. But here we don't care, as we do dp. So let's call the array. So let's do div. Actually, let's put it on the start. Oh, sorry about that. Now I'm gonna tell you the full solution. So let's go to the dp transition formula relation, however you say that. So let's now see how you can compute the dp_j. Sorry, I don't know how I forgot that. Never mind. So I will yes, dp_j. So the relation, actually we need to add the formula however you say it, will be plus j minus 1 for every p greater to smaller than I, and array p greater smaller than array I. So I'll explain right now the relation I got here. Okay, it doesn't look well. Let me make it bigger for you. So this is the main thing, the main relation for dp. dpij will be actually start will be 0 plus dp of pj minus 1 for every p which is smaller than I, and array, let's say that element in position p is smaller than element in position I. Let's see why. So dp of p and j minus 1 will be the count of increasing subsequences adding at index p that have j minus 1 elements. So how does that help? So let's give an example. Let's have the sequence 1, 2, 3, 5, 4 as an example. So So I won't give you right away for every ij. I will just try to help you understand it. So as we said, one possible is 1 to 3, another one 1 to 4, and we'll see how that helps. So we don't need that right now. So let's have a subsequence. As we said dp j minus 1, so we need the subsequence ending at position p. So let's say p equals 3, actually 2 for 0 indexed. Okay, so p equals 2, array p will be equal to 3. So number of counting critic subsequence ending at element 3 at position 2, which will be equal to with j minus 1 elements. So but we don't know j minus 1, so let's put a start I equals 2, actually not 2 because p will be I equals 4 and j equals as an example k plus 1, which k was equal to 3, I think. Yes, or 2, I don't know, 3 I think. So we have here I and j, let's put them together. So we need to find some position p which is smaller than I, and our array of p, let's say, is smaller than array I. So let's find such position p in the array here. So we said I equals 4, so a p possible p will be p equals 2, let's say, because p, let's actually denote the possible values of p. P equals 1 is true, p equals 0 actually position, because array with 0 equals 1 and 1 is smaller than 4, which is array I, which is 4. So let's see, p actually 0, 1, 2 are the possible values for p. So and j minus 1, so let's see j minus 1, which will be equal to, because as we said dp we need dpp of j minus 1. J minus 1 will be equal to 2. So we need the number of subsequences ending at either 0, 1, 2 and having 2 elements. So again, let me write down. So we need dp of pj minus 1 because if you have, let's say we know that, because to compute dpij we need to know the previous values. So we should know dp of p j minus 1. So that means we know the number of subsequences ending at index p. Let's say ending index 1 with j minus 1 elements. J minus 1 elements. So if we know that, we can add that to the result dpij, because let's say we have 2 including subsequences with ending at index p with j minus 1 elements. So that means if we insert in this increasing subsequent ending at index p, one of these two, because we said there are 2 here. Let's say the one subsequence is 1, 3. If we add the element array I at the subsequence, as we know that this element is smaller than or equal to array I, so that means if we insert array I, this will be increasing. As we know, this is increasing. Subsequence 1 to 3 is increasing. 1, 3 is increasing. And as we know, array I is bigger than 3, because we said here array of p will be smaller than array I. So array I is bigger than array p, so that means if we add element array I, it will be also increasing. So that means we have plus 1 subsequence, increasing subsequence, with we had j minus 1 elements here, plus 1 element which is array I, so j minus 1 plus 1 equals j. So we have here j, and the second parameter, And here we have I, because we're ending at index I, at element array I, which is at index I, as all elements are unique. So position of array I will be always I. So that means that we know we have pre-calculated that dp(Fij) depends on dpp of j minus 1, j minus 1. Sorry, I speak Greek sometimes. So let's do another example. I don't know if you understand it. I did some silly mistakes on the back that weren't needed. So let's put that up. So we know this is a relation. Let's do some steps. Like we know this is a relation. So we need to explain why. We know that as we say for every p, we know that p will be smaller than I, and 3 we know that array of p, let's say pi, however you call that, will be smaller than array of I. So that means we know, of course we know because it's dp, we should have known, and we know dp of p j minus 1. So since we know that, we know the number of subsequences, of creating subsequences ending at index p and having j minus 1 elements. So let's say we have dp of p j minus 1 equal to 1. There's one subsequence ending at index p, increasing subsequence with j minus 1 elements. Let's say that is subsequence 1 for 5. So since we have 3 elements, j minus 1 equals 3, so j equals 4. We'll learn that in below. So there is one subsequences in on subsequent Greek subsequence with this satisfying these conditions, the above conditions, ending at index p. So if we need to add array I, so let's say we add array I at the subsequence. So of course this will always be of course this will be again increasing, as we know this subsequence is increasing, and we add array I. So in order to be increasing, we need this equation to, not this equation, this inequality to be true. So 5 will be smaller than array of I, and position of 5 again should be smaller than I, because we need subsequence. So subsequence will consist of positions, let's say I1, I2, I3, which should be all increasing in order to be subsequence. So that means, and we have to these two inequalities, and this should hold. So these two should obviously they hold, as we said in 2 and 3, because I will be always larger than the position the subsequence is ending. So the position subsequence is ending here. 1 for 5 is 5 is the element, so the position is position 5, which is p, the last element, because we say count of Greek subsequences ending at position I, at position p. So we know this is true. So let's put a check on that. Let's say true. And this one is also true because, oh sorry, wrong one. This one is true. We said for positions, and now we need to know if 5 is smaller than array I. 5 is the last element, so it is, let's say, array p, because last element, last position in the subsequence is p. So this I've underlined here is going to be rephrased as array of pi is smaller than array of I, which also holds as we see here. Array of pi, let's say p not pi, is smaller than array of I. So if we know the count of Greek subsequences with j minus elements ending at position p, and that means for every I larger than p, we can insert one more element such that array I is greater than p, than array of p, and make another one subsequences, another increasing subsequence with j minus 1 plus the element we've added, which is equal to j. So now the subsequence ends at index I and consists of j elements, which is equal to this, we have said is equal to dp of ij, which is the number of increasing subsequences ending at position at index I and consists of j elements. So I think we should code it. Sorry, I had a long time to wait to make a video, so I got confused. Let's dp here of, let's say, because this will be actually, we'll see about complexity after. Complexity will be at least n squared multiplied by k. We'll see about that after. So let's start coding. So we have at first a global. We have here what I will underline now. The dp which will be already equal to 0. So let's do now what we need two, as we see. Let's go again here. We need two parameters, let's say I and j. So let's pick every I. Okay, we have picked every I, and then let's pick every j consisting of okay, and you should have a base case, of course. So the base case will be, let's write somewhere here, the number of subsequences ending at index 0 with an element or an ending. Oh my god, I suck at this. So the base case will be the number of subsequences ending at index I with one element will be equal to 1, of course. That sounds good, I guess. Yes. Let's do that right now. So dp of phi 1 will be equal to 1. So let's pick every j that consists of j elements. We need two elements, as we know, one until how many elements? N elements. Yes. Yes. So dp by j plus equal dp of p j minus 1. So here we need to find p. So let's start off brute forcefully. Let's search every p. Let's say k from 0 until I minus 1 actually. And so let's check forever if this index can be a p, let's say. So we need to know if array of p is smaller than array I. And yes, since we know, and p is smaller than I, but we know that, let's put that k. So we calculate that here actually, the dp instantly as we find an index. So let's put that p again. So yes, so here dp plus d, okay, d by j plus equals dpp j minus 1 for every p we find which is valid, with the constraints of p is smaller than I and array of p is smaller than array I. So that is good, I guess. And we need to find for every index the sum of the dp I k plus 1, since we need the number of total subsequences, and this subsequence can end either at index 0, 1 until to n minus 1. So let's do that. k plus 1. Okay, I don't have any way of testing this. I have some problems running here with code blocks, so let's go to an online ID, I guess. Actually, haven't tested that. I came up while making the video of writing code, and I mean some kind of solution. So maybe I was saying things that won't work, but I think it will work. So what am I doing? So let's go. So let's run that. Nice, good start. Fix data. Wait, I put on swan. Never mind. Also, I will answer a question about my age. How old am I? At last on the video. So we had like 5 elements, and I think yes, k equals 2. 1, 2, 3, 5, 4, F7. Okay, that works. I'm good actually. I didn't think that would work. Never mind. So we can optimize that, of course. So that will be the complexity from this code. It will be O of let's say n to the third, which is not very good. So let's try to optimize that. We'll of course do very good with O of n log n on the next video. Oops. With segment 3. Let's do that with st and dp, of course. So let's try to optimize. Of course, we need the first loop and the second loop, I'd say. So we need to optimize the number of elements smaller than array I. The count. Actually, we need to find these elements. So let's try and do that. Now let's get. Okay, maybe. Of course, we'll do the optimal, as I said in the next video with segment 3. At first thought, we think of segment 3 or binary 3 or something like that, structure like that, because we know that we can find fast the number of inversions in an array with binary index 3 or things like that. So we're close to inversion. We just know we need for a number like of pairs with I smaller than j, but array I is smaller than array j. Whereas in the inversions, array I is bigger than array j. If I'm not lied, yes, that's correct. So you can use, I think, that kind of thing in a segment 3. Let's fix the code here. Yes. Okay. So maybe I will do that to the end and do that enjoy problems. How do you? Okay, that's good. don't save, I guess. Okay, so let me think about that. So let's say we have one. Okay, let's do the example 5 4. We need to find, let's say, horizon AI equals 2, which is element 3, the number of pi, let's say p, which is smaller than I, and array of p is smaller than array of I. So let me think a moment about something. Yes, maybe we will do the semi-optimal, let's say, in this video, like to do a segment tree to count that, like inversions, and do the full solution with segment tree and dp combined together in the next video. Or we can do the joy problems. Wait, let me search a little bit about something to see if I'm correct, right? Yes. Yes, as you see, we're using merge sort, we can do that. Or we have, I think, using, yes, binary in 3-bit. So let's see about that. Maybe I think I'll do that and then some joy and stuff like that. Nice. I didn't think the DP would work at first time. Let's go. So yes, we know that. Let's see. So we need inversions, not actually in an array. We need inversions like in a range, in a prefix actually. Um, a lot of advertisements here. A lot of advertisements. Actually, also, do you know that the Geeks for Geeks will be is hosting now currently until January, I think, yes? A contest that you're writing a blog about something geeky, computers and stuff like that. I wrote some hard DP and bit masking question. I'm trying the author to mark it. So let's see what we have here. Yes, let's say on the left side. That works, I guess. Right side, that's it. Oh, we have binary cell balancing, binary search tree. Yes, I have done something like that with AVL tree. I think it worked on HackerRank. Yes, it will be a lot of code we do like that. We can either start with joy problems and I'll write some code on the other screen at the same time for this problem. Maybe I'll show it later. I was just wondering ways to do that. Never mind. So let's go back to join. We have fountain. Uh, I don't know, let me explain really fast. I don't know if you can understand. So you have some like segments. How do you call that? Reservoirs. I don't know. Yes. So each of these reservoirs, as you see, here we have 1, 2, 3, 4, 5, 6 as the numbers here. And each one has some diameter and some length. So we fill with water one of these. Then if it fills up, then the water that overflows goes to the next um, reservoir, which has larger diameter than the first one, than the previous. This one we're currently at. So you have like here, which stores 10 liters, and if we pour 11 liters, then 1 liter will go to the next reservoir with strictly larger, as it says here. I've underlined it. Reservoir strictly larger diameter. And it doesn't exist, it just goes down to the floor, I guess. I don't know, it's fantasy. So this one later, I said an example, will go here on 2 reservoir. But it will never go from 2 to 3 or 4 because it has smaller diameter. So uh, let me discuss the optimal solution, I guess. So it needs, as we need dp, but not just dp, binary lifting. So the solution, I'll attempt to write some filthy code. Sorry for the bad word. Yes. So let's see. So actually, you can comment down below if you didn't understand the DP, because I didn't have it in one shot and I just came up this time I was saying about what will I say, and I will be doing that. Maybe I will edit the video in the future as I'm saying. Never mind. Or if you want me to do another video for DP and explain that specifically and other problems. So let's go back to this problem. Let's discuss the solution. Okay. Yeah, discuss right away the solution. So right away we see that in the input we have some queries that ask us, we have two numbers, let's say x and y. X is the reservoir we're given where right now, and the liters, y is the liters that we have poured right now on it. So it means if x is bigger than the liters that it can hold, x reservoir, then it will flow down the remaining liters, will flow down to the next larger with larger diameter reservoir. So the solution here is to construct a tree which will do binary lifting on, binary jumping as some red coders say. So yes, we will do construct a tree where we'll put an edge between a node and let's say a reservoir, and the next strictly larger reservoir with larger diameter. I mean, we'll put an edge to that. So that means from a node, the the let's say if it overflows with liters, then this extra liters of water will go to its parent because we have put an edge to the strictly larger. So let's draw that, I guess. Okay, I'm not good at drawing again, sorry about that. Let's see, we have that and that and that, that and that and that and that. Sorry about a lot of that. So That means that if we pull, wait, let me think about something. Yes, it means that if we pull from this node bigger amount of liters than it can hold, let's say it can hold L, so it's bigger than L, then this liters, let's say it holds X, actually we said L, so let's say we put X, so if X is bigger than L, so the remaining water, X minus L, will go up to its parent here, which if it overflows will go here, will go actually nope, I don't go there. If it goes here then tenth, because here it's like the end, because here you can't go because this leads to here, so it's like one directed tree, let's say, which isn't actually. This goes here, this goes here, everything goes up, let's say. So like this is a last fountain. Yes, this will be 3, and as we construct this tree, we'll binary on it. So how can we find the next larger with diameter fountain reservoir? We can do that with stack. We can search that. It will be easy actually if you think about it or if you know it. So we can do that with stack. So we can construct the tree using the stack to find the next larger element. Let's say. Sorry about the bad drawing. Let's clear it. So we'll construct the tree. And then let's write. So as we know, the relation will be for binary lifting is dp of, sorry, I was loud, dp ij minus 1 j minus 1. So okay, I should have left it, never mind. You can see many codes of binary lifting. It's really cool, I like that. So I don't know, I won't explain to you binary lifting and that stuff. There are a lot of articles and blogs, videos about that. I'll just say that dpij, the relation will be the 2 to the jth parent of I, and we go like as powers of 2, we go to 2 to the jth, let's say, to 2 to the third, let's say, then we add 2 to the fourth parent, so we are now at the 2 to the third plus 2 to the fourth parent, and we add with powers of 2, and it's really good actually. So classical problems are kth ancestor, like that, LCA, you know that, I think. So we should like modify, it's easy actually, at least all we need to do is know binary lifting and construct the tree. So we need to know the stack and set things to find the next largest element. So we construct the tree. Actually, going to write code, maybe I will send you in the comments down below. I'll send you a link or something like that. There are solutions on the site, I think, yes. So you can read more about that here. I will just explain briefly. So yes, so we construct the tree. That's like hard part, I don't know. And so in the binary lifting, it just is. We just modify the code. We do the classical always the relation. I just wrote 2 minutes before, and then we just modify the code like for kth ancestor to find the large, let's say the parent, the ancestor, like the largest ancestor. I mean the highest ancestor. Okay, I wrote it wrong. Sorry about that. The highest ancestor, let's say, from a node which sum of letters is bigger than the ones we're given. I said the example x and y, so it's bigger than x, because if it's bigger than x, then it can hold x. So the last fountain we're at can hold x. So if it doesn't exist, then -1 or 0, whatever the problem says. I think 0, don't know, -1 maybe, I don't care, sorry. Yes, so, but you know, it's not that hard. If you know, like, if you have done binary lifting and such stuff, you can see the code for that and try to think a little bit. Yes, it didn't took that long. Nice, 45 minutes. We're good. So I said that we're gonna discuss two problems. I don't know where the other one is. Maybe in the, because yes, I have it here. The other problem, but yes, I thought I was gonna do that. Some with segment and lace, you know, FDP, but I don't know if I have time enough. I mean, I don't have enough time. So maybe another video. So I will try to do some. I think we understand this DP. I'll try to do uh, some coding about finding the optimal, actually the number of elements smaller than array file, let's say, as we said in the first problem. Yes, I think that's all. So make sure to subscribe, please. And I'll see you in the next video. Goodbye.